Okay, so now we're going to look at the degenerate case. Let's do it with a quick example. Let's look at A is 1, 1, 2, 0, 1, 0, and 0, 0, 3. So I'm not interested in the case where the eigenvalue is 3, it's 1. And if I have a quick look at that, you discover that the only eigenvector that works is 1, 0, 0. There is a corresponding, let's get rid of the 1. There is a corresponding row eigenvector, which is 0, 1, 0. That's the only thing that works when you try and solve the problem. You can clearly see that, right? Because I have to solve A minus I times the eigenvector is 0, 0, 0. And that matrix is going to be 0, 1, 2, 0, 0, 0, and 0, 0, 2. Subtracting 1 from the diagonal, right? So this times my eigenvector has to be that. The only thing that I don't get is something in the first element. The second two have got to be 0. Okay, so that's a case where we've only got one eigenvector, right? And you know, typically one is used to dealing with as many eigenvectors as there are rows or columns in the matrix, so this is an awkward setting. At first sight, it seems to be okay, because it means that I don't have this issue that came up last time, which is that there are different possible solvability conditions to take. Clearly, there's only one. Now, that's okay, but you'll notice that E, dagger, with the product with E is 0. These things are orthogonal. Now, that's definitely a problem, because the correction for the eigenvalue that we calculated, we had a formula for it. It had that numerator, and it had exactly this in the denominator. So this doesn't exist anymore. Okay, so the methodology that we've derived is not going to work in this situation because these two are orthogonal. So what can you do instead? Now, just to go back a second, we started the course by talking about algebraic problems, and we had these polynomial problems where we were looking at roots. And you know, we developed these strategies for figuring out how to perturb the roots, get the solutions. One of them that we dealt with was a funny one, because we had a problem that it was a quadratic equation. The solutions at leading order were equal. And then when you added the perturbation, you split the roots. And as a result of that, it was like a singular perturbation. And you got a correction, which was the square root of epsilon. So you got a fractional power of epsilon. Now, of course, when you are dealing with eigenvalue equations like we're dealing with, you could just abandon the eigenvector part of it and just look at what you do to the eigenvalue. And the eigenvalue satisfies the characteristic equation, which is a polynomial equation. So if I was just to focus on the eigenvalues, I'm really doing the same problem that we did before. And so there's this funny situation that I ought to be then expecting, where the leading order problem has two solutions that are the same. That's repeated eigenvalues, but then when I perturb them, I should expect fractional powers of epsilon. And clearly we've not dealt with that situation yet. And however, I'm bringing that up, and you might well suspect that it corresponds to this situation. If we are going to carry on and attack this as a matrix problem, though, we need a bit more technology. So I need to talk about generalized eigenvectors. So let's imagine that I have a repeated eigenvalue, A, and it's repeated R times. Right? If it's degenerate, and there is only one eigenvector, we may define some generalized eigenvectors. Now, when you're doing linear algebra and you're doing all of that kind of stuff, maybe you're doing this because you need a full complement of vectors. You want to span some space. So if it's n by n, you want n independent eigenvectors in order to deal with things. So you know, your eigenvectors here, there's just one of them. So you're lacking enough vectors to make up a basis for your space. So you invent more in order to make it work. So that's why you might have encountered this kind of thing in the past, and that's how it's useful in certain other contexts. So let's define what we have here. So we've got a matrix, and then we have an eigenvector. So let's call this E1, and it satisfies that equation. Now, it turns out that if this particular eigenvalue is repeated r times, but there's only this one eigenvector, then I can define a whole bunch of other eigenvectors, r minus one of them, by the following. So I can get an E2 by making it satisfy this equation. So instead of satisfying the eigenvalue problem, it's the eigenvalue problem plus a little bit, namely E1, and then there's an E3, which satisfies the same thing, except there's an E2 in there, and this goes all the way down to ER, which satisfies AER plus ER minus 1. Right? So there's a whole bunch of eigenvectors. These are all of the generalized ones that I'm adding into this one so that I get R vectors. Okay? So I can define these things. That's a bit of additional technology that we're going to need. All right, so let's just have a quick look over here and see what these generalized eigenvectors are in this particular case. Okay. Right. So that's E1. Now, I've got this matrix, so I've got A, E2 equals little a is 1, so this is E2 plus E1. So that's this equation now, right? Now, I can verify, and I can just do the math if I wanted to, just do a little bit of algebra. I can verify that E2 here, 0, 1, 0, satisfies that. So that's a generalized eigenvalue, eigenvector that satisfies this problem. Okay, so here's an example of making up a full complement of eigenvectors by generalizing how you calculate them. Right, there's the first one. This is an independent vector. It looks good. Right, so that's how you can do it. Let's do another quick example. Let's do A is equal to 0, 1, 1, 0, 0, 1, 0, 0, 0. In this case, A is equal to 0 is repeated 3 times. Repeated thrice. Okay, you can verify that E1 is equal to 1, 0, 0. Okay, so that's satisfying this equation. Then A times E2, since little a is equal to 0, I need an E2 that satisfies that. And I've forgotten to write that down over there. You can quickly verify that E2 is 0, 1, 0 again. So let's just double check. If I take this and multiply by this matrix, I get 1, 0, 0, which is that. So this is good. And then there's the AE3. So AE3 has to equal E2 here because little a is 0. Just doing a little bit of algebra. You can verify that E3 I can take 0, minus 1, 1. Right, so that'll satisfy that equation. Right, so here we go. We've got all of these different cases. So I'm just going to pop these over here for my enjoyment and use later. All right, so 2 examples of how you can generalize your set of eigenvectors with these extra things so that you have a full space. Great. How can we then use them to solve the perturbed eigenvalue problem? Okay, well, let's just have a quick look at what would have gone wrong had we gone through the usual business here. Right, so I've got AX is lambda x plus epsilon bx. That's the equation we're dealing with. Now we've got A x naught is lambda naught x naught. A x1 is lambda naught x1 plus lambda 1 x naught plus b x naught. And that's putting in lambda is lambda naught plus epsilon lambda 1 and so forth, and x is x naught plus epsilon x1 and so forth. Okay, so what I do here is to change this, bearing in mind that this tells us that lambda naught is A and x naught is E. Then I rewrite this so that I get x1 on the left is lambda 1 E plus B E. That's the equation. The solvability condition now comes from using the row eigenvector. The trouble, of course, is that E and E dagger are orthogonal, so that when I do that product, that term disappears, and then I get a contradiction. Because in general, this times E multiplied by E dagger is not going to be 0. So that's what goes wrong. So the problem is sort of connected to the fact that when I first try and take a solvability condition here with this term, E dagger E vanishes. So this term sort of is not a problem. This term is. Right? This has given me something when I do the E dagger product, but this term doesn't give me anything. So actually, this is a good guy and that's a bad guy. So let's redesign things. And I've already said that maybe there's something wrong with the expansion because maybe we should be expecting a different expansion in fractional powers of epsilon. So let's do that. Let's try lambda is lambda naught plus epsilon to the 1/2 lambda 1/2 plus epsilon lambda 1. And x is x naught plus the same sort of thing. So let's try that instead. Plugging things in, I still get this at leading order. That's the epsilon to the 0 terms. However, because I've now included these things, I'm going to get some terms with epsilon to the 1/2 in them. So what do I get? Okay, so I get A minus AI times x 1/2 equals lambda 1/2 times x naught. Putting this expansion into the whole thing there, right, there are some 1/2 subscript terms, and there they are. This term doesn't yet come in. Now, normally, I'd be worried about the thing on the right here because that matrix is not invertible, and I'd do the dot product with E dagger in order to, try a solvability condition. However, as we have just observed, this is E, or maybe you should call it E1, bearing in mind that we have these generalized eigenvectors. So I'm putting lambda naught is A, and x naught equals this one true eigenvector. All right, there it is. And I don't have to enforce a solvability condition on this because when I take the product with that thing, this thing vanishes. So I can solve that. There's no problem solving for x 1/2. So this is going to equal something. It's going to be non-unique, right? Because we're in this situation where we've got a non-invertible matrix there, but we can solve it. the solution is not unique. And in fact, there's always going to be something, let's call it C1 half times E1. There's always going to be some multiple of the original eigenvector in there. That's the bit that's not determined. And then there's going to be something else in there, and there's a lambda to the 1/2 there. So the particular solution here is going to be proportional to lambda 1/2. And then I just use this technology of the generalized eigenvectors, because I know that A minus AI times E2 is equal to E1. All right, A minus lambda I times the thing that I need is lambda 1/2 E1, so I'm just going to multiply this by lambda to the 1/2. So I see that x2 is going to be lambda 1/2 E2. So that just solves this particular problem. So the particular solution is nothing more than my generalized eigenvector. Okay, right, so for the problem that we were doing here, what do I get? So this is E1. E2 was 0, 1, 0. So what I find is that x1 half is actually some constant, let's call it C1 half, times E1 plus lambda 1/2 E2. So I can solve it. It's non-unique, but I'm still fine solving it. Okay, that's somewhat disappointing, because I just now realize that I've gone to the corrections and I've not been able to calculate the eigenvalue correction lambda 1/2. Lambda 1/2 is whatever it is, we don't know what it is yet. So we need to keep on going at this point. So we need to go beyond this particular order now. So let's carry on, and we're going to go to epsilon to the 1 now. So let's write down the equation for x1. So when you do this, of course, because you go into higher order, you're starting to get more and more terms. So the equation is going to get longer and longer. Now, in the problem that we're doing, with this epsilon to the 1/2 in it, I'm going to get this term at epsilon to the 1. So let's write down what we get. I get my x1s, these terms. Then I'm going to get a lambda 1 x0 plus a lambda 1/2 x1/2 plus b x0. So those are going to be the terms that I get. So previously I just had a term with the lambda 1/2 in there. Now I've got 2 extra terms. So I've got 3 terms on the right rather than 1, as in the previous epsilon to the 1/2 set of terms. Okay, let's fill everything in. So I've got A minus AI x1 equals, so it's lambda 1 times E1, that's what x0 is. Now I've got, this is x1/2, so let's put that in. So it's plus, so it's lambda 1/2 C1/2 E1 plus lambda 1/2 squared times E2 plus B E1. Okay, now there's going to be some issues about solvability, all right, because if I take everything on the right here, when I do the dot product with that thing, when I do the product from the left with that thing, then I'm certainly not going to get 0 for every term. In particular, that one's definitely going to appear. There's still this orthogonality between these two, so that one's going to disappear, that one's going to disappear, but these two won't disappear. At which point I suddenly realize that I've now got another equation. This time it's for lambda 1/2. So let's just have a quick look at what that is. So I'm now going to take the Fridholm alternative. I'm going to take my equation there. I'm going to multiply by the row eigenvector, get rid of as much as possible. What do I get? I get 0 equals, that's orthogonal, so I get lambda 1/2 squared E dagger E2, right? E dagger E2, that's 1, that's not 0, plus BE with an E dagger. So there's the equation for lambda 1/2. And now I'm done. All I'm seeking to achieve is to calculate the eigenvalue correction. I just have to fill in the numbers and I'm done. So this tells us actually that lambda 1/2 squared is minus this thing. So for B, I was using 1, 0, 0, 1, 1, 0, 1, 1, 1. That was my B. So B times E is 1, 1, 1. So BE is 1, 1, 1 times this. That gives me 1. Take it to the other side of the equation, I get minus 1. So lambda 1/2 is equal to plus or minus I. So in other words, lambda is equal to 1 plus or minus I times epsilon. It's complex. But here are the two split eigenvalues as a result of the perturbation. At this stage, if I wanted to, I could now carry on and I could come back to this equation and try and solve for x1. Just like over here, I solved for x1/2. And then, to keep on going, if I really wanted to now figure out what lambda 1 was, that's the next term in the series, the epsilon lambda 1 term, then I'm going to have to go to next order and apply solvability there. That would now tell me what lambda 1 is. So lambda 1 is not going to be determined until I go to epsilon to the 3/2 here. Okay, so given all of that, let's just pause a second. I've now dealt with that particular example. This was an example where we had a multiplicity of 2, but it was degenerate, so there was only one true eigenvector. When I talked about generalized eigenvectors, I actually wrote down another example where the multiplicity was 3 and there was only one eigenvector. So now let's have a quick look at that case. But before doing that, I should give you the general procedure. So we have fractional powers that are cropping up. You need to revise your expansion accordingly, but what exactly is the fraction that you should be using? That's the key question. So clearly, when the multiplicity was 2, we used the square root of epsilon. So the fraction was 1/2. What's the more general thing? Well, here it is. If A is repeated r times, we need the series in epsilon to the 1 over r. Now that's when you only have one eigenvector. I'll come back to that at the very end, but we're almost there. Okay, so this other example. We will do A is equal to 0, 1, 1, 0, 0, 1, 0, 0, 0. B, let's put as 100, 1, 1, 0, 1, 1, 1. We've got E1 is equal to 100. E2 is equal to 0, 1, 0. E3 is equal to 0, minus 1, 1. And E dagger is 100. Sorry. 0, 0, 1. So that's the matrix technology that we're going to need. So So we're going to say that we have A x is equal to lambda x plus epsilon bx. We're now going to introduce the expansion. Lambda is lambda naught plus epsilon to the 1/3, lambda 1/3, plus epsilon 2/3, lambda 2/3, and so on. And similarly, x is x naught plus epsilon to the 1/3, x 1/3, and so on. So I plug in, okay, epsilon to the 0 terms. I get A x naught is lambda naught x naught, and I choose x naught to equal E1. Sorry about that. And I choose lambda naught to equal A, which was 0. Okay, so that's the leading order. Now I go to 1/3 powers. And I get A of x 1/3 equals lambda naught x 1/3 plus lambda 1/3 x naught. This is actually 0 because lambda naught is 0. And I have the equation satisfied by E2. A E2 is equal to E1 here because the eigenvalue is 0. And in other words, I can just read off, since x naught is E1, I can read off the fact that x 1/3 is equal to lambda 1/3 E2. Okay, that's just like what happened before. Now I'm going to go to epsilon to the 2/3, and there we get the following equation. We get A x 2/3 equals this thing again, lambda naught x 2/3. So that's just 0. Now I'm going to get lambda 1/3 x 1/3 plus lambda 2/3 x naught. And I still haven't got to the B bit. The perturbing term's still not appeared. Okay, all right, so what have I got here? This is from there. Oh, I should bear in mind that there's also, let's write it as an arbitrary constant times E1. So this I put into there, and this is once again E1. Right, so this term in here and this one, they both have E1s. So I can write x 2/3, it's going to have, well, it's going to be lambda 1/3 c 1/3 plus lambda 2/3, and the bit that has an E1 on the right-hand side, I'm just going to use this again, so I get an E2. But then in here, there's also this term, so that's lambda 1/3 squared. And there's an E2 in there, but I remind you that A E3 is equal to E2. That's the other generalized eigenvector equation. So I can just simply put an E3 there to get the solution for x 2/3. So I go through, I've calculated x 1/3, x 2/3. There's not been any need for a solvability condition at this stage. And in fact, the perturbing term has still not appeared. It's only when the perturbing term appears that I'm going to need to do something. So let's go to epsilon to the 1. That's where it all appears. I get A x1 equals lambda naught x1, which is 0. Then I get lambda 1/3 x 2/3 plus lambda 2/3 x 1/3 plus lambda 1 x naught plus b x naught. So I get all of those puppies. Okay. Okay, now this is the row eigenvector down here, by the way. But you'll notice that E dagger dot E1 is 0, and E dagger dot E2 is also 0. The only one that's not 0 is the product of E dagger and E3. Right, this is this thing, and it was 0 minus 1, 1, which gives 1. So this is 1. Okay, now in this equation, that means that when I take this equation and I multiply on the left by E dagger, this goes away. Now, that's just an E1, so that's going to go away. X1/3 here has got an E2 and an E1. But the dot product of both of those vectors with E dagger is 0. So that's going to go away, that's going to go away, that's going to go away, that's going to go away. So the only ones that are going to survive when I now take the Fredholm alternative are these two. So using all of these orthogonalities, we'll finally arrive at the following. Okay, almost there. So we get 0 equals, so lambda 1/2, lambda 1/3, E dagger and an X 2/3, plus lambda 2/3, E dagger X 1/3, plus lambda 1 E dagger, that's E1, plus E dagger B E1. Right, so that's 0. X3 contains E1 and E2. Don't give me anything there. And if I now pop this lot into here, the first term there, that's an E2. That's orthogonal to E, so this doesn't contribute. The only one that contributes is this one. So we get lambda 1/3 cubed, and E dagger dot E3 is 1, plus whatever I get from here. So this is 0, 0, 1. The matrix was 1, 0, 0, 1, 1, 0, 1, 1, 1. And E1 was this. So this is 1, 1, 1, 1. Doing that, I'm going to get 1. This thing has to vanish. So in other words, I get lambda 1/3 cubed is equal to minus 1. So the solutions for lambda 1/3 are the cube roots of minus 1. There's 3 of them. 2 of them are complex. 1 of them is real. Anyway, there it is. So that's the answer for lambda 1/3. So that's the beginning of the series for the solution for the eigenvalue. You can calculate the eigenvector corrections at this point. To get the next term in the series, the lambda 2/3, this thing, you're going to have to do more work. You're going to have to apply a solvability condition at next order. Anyway, this is how it works. So let me just briefly conclude. Just wipe the board. I've given you a recipe now of how to deal with situations where you have repeated eigenvalues and you either have a full complement of eigenvectors or you just have one. Now, if you have a multiplicity that's more than 2, then there are obviously other situations as well. Because let's say I had a multiplicity of 4, then there are exactly 4 possibilities. With a multiplicity of 4, I could have 4 eigenvectors, or I could have 3 genuine eigenvectors, or just 2 or 1. So you go from one extreme to the other, a full complement or just the one, and all of the cases in between. So what do you do in those cases? Well, you have to make up an expansion that suits how many eigenvectors that you have. So let's say that you've got A repeated R times. If you have R eigenvectors, you need a series in epsilon, and you're going to get a new eigenvalue problem. For the coefficients of those eigenvectors. If you have one eigenvector, you need a series in epsilon to the 1 over r. You need to expand r times. You need to go through r equations until you finally get the perturbing term coming in, at which point you finally find the leading order eigenvalue correction. So you expand a lot. Eventually, when the epsilon bx term enters, solvability gives lambda to the 1/3. And you need to use all of these generalized eigenvectors. Oh, 1 over r, I mean, in the general case. Right, now if you're somewhere in between, unfortunately you're going to have to do something in between these. You're going to need some fractional power of epsilon that corresponds to how many eigenvectors you actually have. So it gets a little bit elaborate in between, but in principle you can figure out what you need to do and put it in and solve the problem. Okay, so at that particular stage I'm now done with the third segment.